balancing redox reactions. And you thought that balancing chemical reactions was easy peasy. Competency M1, so easy, right? Well, you're in for a treat. Take a look at this redox reaction here. 1 Ag on the left, 1 Ag on the right. 1 Cu on the left, 1 Cu on the right. It's perfectly balanced, right? This is an unbalanced redox reaction. Now remember that for redox to occur, a species needs to lose electrons, and those electrons go somewhere. And so for that reason, a redox reaction is made up of two half reactions, one oxidation, one reduction. Let's take a closer look at this overall redox reaction. Silver on the left has a charge of +1, on the right it is 0. This is a gain of 1 electron. Copper on the left has 0 charge, copper on the right has a 2+ charge. That is a loss of 2 electrons. Currently, this reaction is unbalanced because we see that Ag only has room for 1 electron, but copper has to give up 2 at a time. So what we do here is when we balance redox reactions, we're actually talking about balancing the number of electrons. Okay? For half reactions to perfectly complement each other, the number of electrons transferred and gained must equal to each other. So what do we do? Well, if copper must lose 2 electrons at a time and silver can only gain 1, that must mean that the silver half reaction must run twice for every time the copper half reaction runs. So to show that the silver half reaction is going twice, we just simply put a 2 in front of both Ags. Why both Ags? Because conservation of mass, we still have to maintain equal numbers of atoms and elements on both sides of the arrow. But now we're just saying we're also going to pay attention to the number of electrons transferred to make sure that those are equivalent for the oxidation and the reduction half reactions. So that was quite straightforward, wasn't it? Well, it's only because we're looking at singular elements, right? We got single atoms to look at here, super easy, but of course, in actual chemical reactions, we are dealing with not just elements and atoms, but compounds as well. So let's go over how to balance those. Let's have a look at some examples on how to balance redox reactions. Once again, we're not interested in only balancing elements from left and right side of the arrow. We're also interested in balancing the number of electrons transferred for redox and oxidation half reactions. So there are two main methods to balance a redox reaction. The first one is using what we call a half reaction method, and the second method is using the oxidation numbers. This lesson will only focus on the method which uses the half reactions. The half reaction method is longer. You gotta write more stuff down. It's kind of tedious. However, it is the more safe of the two methods. You are less likely to make a mistake. So we'll do this one first, and if we have time, we will do the other method. All right, it goes like this. Step 1. Break apart the overall redox reaction into its individual halves. Okay. How do we know what is happening in each half? Basically, we look at the elements. There's a manganese here and a manganese there. Those two must belong in the same half reaction. There's a carbon over here and a carbon over there. Those must belong in the same half reactions. So first step, we're going to split them apart. MnO4 minus 1, whoops, turning into Mn. And the second one is C2O4, 2 minus, turning into CO2. All right. Second step, we take a look at our two halves, and we're going to balance the elements first. Because remember, in balancing an equation, the very basic thing you should do is make sure that the conservation laws are upheld. In the first half reaction, oh, I'm sorry, I forgot to mention, we're only looking at non-oxygen elements when we do this step. In the first half reaction, we see manganese and manganese. There's one on each side. We're good. On the second half reaction, there are 2 carbons on one side and only 1 on the other. We're going to go ahead and drop a 2 on the right side. Drop a deuce. Oh. That's it for step 2. Okay. Step 3. We will now balance the other elements. Okay. For oxygen, we see on the left here for the Mn half reaction, there are 4. So we need 4 more oxygens on the right side. Now this is where it gets complicated because we can't just put in some oxygen. That would kind of change the nature of this chemical reaction. So instead, we're going to think hard about where there are oxygens already available in such a system. Remember that in most of these reactions, water is present. Most of these reactions are occurring in the aqueous phase. So to balance the oxygen, all we got to do is express the water that is already starting in the system into this equation. And there it is. Why 4? Because if I add 4 waters, I will get 4 oxygens on the right side. Okay. For the second half reaction, we can do the same thing. On the left, we have 4 oxygens. On the right, we have, 4 oxygens. We're good. Moving on. Now, the next step is to, again, balance the elements. We just keep going. On the first half reaction here, I added 4 waters. Well, that also means that I introduced a new element, hydrogen. I got 8. So we're going to have to add 8 hydrogens on the left side. And once again, we're not just going to add H2 gas. That's a different scenario. We're going to pull the hydrogens from something that's already available in the system. Remember that water exists in equilibrium with itself. Water turns into H plus and OH minus. So H plus is already present in the system. That is what we will include in our half reaction to balance. Okay, so now that all the elements are nicely balanced, now we balance the charge. Balancing charge is a little bit more tricky. I'm going to start with the second half reaction because that one is easier. Notice how on the left side we have a -2. And notice on the right side how we have 0. So in order to balance the charge, we're going to add 2 electrons on the right side, such that now both sides have a total sum of a -2 charge. Now you may be wondering, why did I add 2 electrons and why didn't I add like 2 protons? Well, because protons are not part of our redox discussion. Remember, redox is just gain and loss of electrons. And as well, protons are a bit more tricky. They don't really free flow in space. Well, I guess you could argue hydrogen. You could argue, why don't we just add 2 hydrogens and both sides will add up to 0? But if I did that, I would have to add some more hydrogens on the right side, and then it just perpetuates. You would just never finish that equation. Okay? So only add electrons when you try to balance the charge. The first half reaction is a bit more complex because we see charges in multiple places. We have 8 pluses plus a negative. So the total charge on the left-hand side is 7 plus. Okay. On the right-hand side, I just noticed I forgot to transfer the 2 plus down here. On the right-hand side, we currently have 2 plus. So how do we make sure that both sides are equivalent? Well, we could add a -5 on the left side such that the total sum becomes +2. And that's what we're going to do. We're going to put 5 electrons on the left-hand side. So now what I have are 2 half reactions that are fully balanced in terms of elements, atoms, and charge. And now when we look at these 2 half reactions, we can figure out what therefore must be the balancing for electrons. If the first half reaction needs to receive 5 electrons to go, and the second half reaction releases 2 at a time, how many times of each half reaction do we need to run before they are perfectly coupled together? LCM, lowest common multiple, and there you were in math class thinking that you will never use that concept in your real life. Well, most things you learn in math class will support your science education. So what is the lowest common multiple between 5 and 2? Hopefully you're going to say 10. So that means that the top half reaction is going to run twice for every 5 times the bottom half reaction will run. And now we're just going to add the 2 together to get our final fully balanced redox reaction. So now we just foil. We just do the foiling, okay? All right, here we go. 2 times 5 electrons is 10 electrons. I'm actually not going to write this one down because later I see that I have 5 and 10 electrons. So if you did write it down, it's okay. But when you add your reaction, you can notice you can get 10 electrons on both sides, which you just cancel. So I'm just not going to bother writing that down. So let's FOIL. 2 times 8 is 16 H pluses plus 2 times Mn04 minuses. Okay. Now let's move down to the second half reaction because I want to list everything on the left of the arrow first before I list things on the right. We have 5 times C2O4 2 minus. Now that I'm done with all my species on the left, I can do my species on the right of the arrow. 2 times Mn2 plus 8 waters plus 10 CO2s. Great. And there you have a balanced redox reaction. Let's try another one. You may try first and pause the video, or you can go along with me. All right. First step, break it apart to its individual halves. Okay. All right. The 2 chromiums. Here we go. Cr2O7 2 minus turning into Cr3 plus. This time I'm just doing 1/2 reaction at a time. Maybe it'll be more clear. Okay, I see there are 2 chromiums on the left. I need a 2 on the right. Ooh, that's an ugly 2. Now I balance the other elements. I see that I have 7 oxygens on the left. I'm going to need 7 oxygens on the right, so I'm going to add 7 H2Os. By adding 7 H2Os, I've also added 14 H's. So on the left-hand side, I'm going to put 14 H's. Now that all my elements are balanced, I will now address the charge. I got 14 plus minus 2. That is 12 plus on the left. I got 2 times 3. That is 6 plus on the right. So to make the 2 sides have the same charge, I need to reduce the 12 into 6. And so the left side gets 6 electrons. Okay? Or actually, more accurately, I should say, in this half reaction, it is a gaining of 6 electrons. All right, second half reaction. I2 turning into IO3 minus. First, balance the elements that are not oxygen. I got 2 I's on the left. I need 2 I's on the right. Next, balance the oxygens. I got 3 on the, actually I have 6. Oh, good catch, Miss Goo. 6 on the right. I'm going to need 6 waters on the left. By adding 6 waters, I've now introduced 12 hydrogens. So I will add 12 hydrogens on the right. Now I can address charge. I have 0 charge on the left, and I have minus 2 plus 12, that is 10 plus. How do I make 10 plus equal to 0? Easy, I'm going to add 10 negatives. On the right hand side, we put 10 electrons. Great, and now we go back to the LCM. We have 6 and 10. Hopefully you're not doing 60. That would just be ridiculous. The lowest common multiple would be 30. The top one runs 5 times, the bottom one runs 3 times, and now we're going to add them all together. You can do this with as much work shown as you want, or you can shorten this if you're really good at just thinking all in your head and keeping track of all the numbers. What I mean by that is, I see that I have a 5 times 14, and I have a 3 times 12. So 5 times 14, feel free to use a calculator so you can do this faster. 14 times 5 is 70. I'm going to end up with 70 H's on the left. And then 3 times 12 is 36. I'm going to end up with 36 H's on the right. So at the end of the day, when you cancel things that are the same on both sides, when you simplify your numbers down, you're going to end up with 70 minus 36. You're going to end up with 34 H's on the left. Okay, So you can do this in your head, and you can just go ahead and write 34 H's as you're starting. Or what you can do is write everything in full and then cancel as you see it, all of it in front of you, okay? Whichever you prefer. Okay, 34 H's plus 5 Cr2O7 2 minus plus. And again, we have another situation where there's two things, one on the left, one on the right, that are the same. I'm going to have 35 waters on the right. I'm going to end up with 18 waters on the left. 35 minus 18 is 17 on the right. So I'm going to skip this term and just move on to I2. Okay. All right, moving forward, 10 Cr3 pluses plus 35 H2Os. Oh, but remember, I already canceled that because I put the, oops. I remember I calculated there's only 17. 17 waters and 6 IO3s. And this thing here, I've already taken care of. I reduced it already down to 34 on the left. The net number. All right, and now that is the final answer. Charge is balanced, elements are balanced as well. Our last example is slightly different. There's a bracket that says basic. No, it's not a basic question. It's not easier. Sometimes a chemical reaction cannot occur under acidic conditions because of where and how it's happening in industrial processes. You may have noticed in our previous two examples, our final answer had hydrogen ions in them, which means that for the reaction to go, you actually have to run it in an acidic condition, such that there is a healthy supply of hydrogen ions. All right, so for whatever reason, sometimes the industrial process cannot occur under acidic conditions, and so we just do a little adjustment at the very end to make sure that we understand how the reaction can proceed without the presence of hydronium or hydrogen ions. Okay, so the first few steps are the same. We figure out what the half reactions are, and this is iron 2 hydroxide turning into iron 3 hydroxide. The second half reaction is CrO4 2 minus turning into CrOH 3. Okay. Balance the elements that are not oxygen or hydrogen. That's done. Balance the oxygens. Okay, first one. We have 2 oxygens versus 3 oxygens. To balance that, we're going to add 1 water on the left. By adding the 1 water on the left, I have added 2 H's. There were already 2 H's present in that first compound. That's 4 H's total. On the right side, I have 3 H's, so we only just need 1 H plus on the right-hand side. Now we balance the charge. There's no charge on the left, plus 1 on the right. We add 1 electron. On the second half reaction, we have to add 1 water on the right so that there are 4 oxygens on both sides. And then we add 5 H's on the left. So there are 5 total. How did I get that? Well, 3 plus 2, 5 H's. The total charge on the left-hand side is 3 plus. The right-hand side is 0. So we also add 3 electrons on the left. To look at how these two half reactions will couple, we have to run the top one 3 times in order to produce 3 electrons to feed the second half reaction. Now let's sum them all together. Foil time! 3 waters, but there's also a water on the right. So which means I spend 3 waters, I make 1 water, which really means I only have to spend 2 waters. Once again, you may do this in full. I'm just skipping some steps because I'm lazy and don't want to write more than what's necessary. All right, plus 3 FeOH2 plus 2 H pluses. I know there's 5 here, but there's going to be 3 on the right. So the net effect is 2 remaining on the left. Plus CrO4 2 minus, giving us 3 FeOH3. The H, this H here is gone. I took care of that already. All that's left is CrOH3 because I've also already taken care of that water. Okay, so now we do our basic adjustment. We cannot have this 2H plus there, so we will replace it instead with OH minus. Okay. So the way to neutralize 2 H pluses, you can think about it this way, is to add 2 OH minuses. Okay? If I add 2 OH minuses, what does that become? What does 2H plus 2 OH minuses get you? Oh, buddy, that's just water. Wow. Okay. Now, if I added 2 OHs on the left-hand side, I have to also add 2 OHs on the right-hand side because conservation laws. All right, so that's the adjustment. That's it. I've now changed this acidic equation into a basic equation. All that's left is to just tidy up and just rewrite everything so that my final answer is very organized and clear. Okay. All right, so you may notice now that the 2 waters I just made, well, there were already 2 waters on the left-hand side, so let's just combine the 2. Let's combine the 2 and just change that coefficient to 4. Okay, and then the rest is just the same. Okay, here we go. Oh, we're almost there. Oh, we're almost there. Oh, I can feel it. Oh, yes, and we're done. The final equation is now under basic conditions because we have OH minus instead of a H plus. And that's how you balance redox reactions. Holy smokes, the process is long. Please go ahead and try the 3 examples on the next page. There's one that's basic for you to try. Okay, the answers are coming up. Don't look until you've tried. Here are the answers. The final answer to all 3 questions are highlighted in orange. Hopefully you got them all right. Goo out.